When we first started learning physics and doing kinematics, our goal was to predict an object's trajectory by integrating its acceleration over time. That told us what the object's velocity was, and integrating the velocity would tell us what its position was, and then we would be done. But as we first saw in the case of circular motion, acceleration isn't always given to us as a function of time. In many systems, acceleration is instead a function of position, and that means we have to approach these systems in a different kind of way. One of the most relevant examples in the real world, where we know an object's acceleration based on its position rather than time, is in the case of oscillating systems, or in particular systems that exhibit simple harmonic oscillations, and we'll get to what that means in just a minute. But for now, let's talk about the basics of oscillatory motion. Consider the pendulum on the left side of the screen here. It's one of the most basic oscillating systems you can imagine. Just grab a piece of string, attach a mass on one end, and hold it by the other. So what happens to this pendulum once you lift up the mass a little bit to the side and release it? Well, as you can test for yourself, gravity is going to act on the mass and pull it back down towards the vertical position. We call this position, when the ball is vertically aligned, the equilibrium position, because if you just placed it there without having it move at all, it wouldn't start moving. That's what equilibrium means. But in our case, the mass wasn't placed in this equilibrium position, instead it's swinging through it. And so it doesn't just stop, but instead it continues until it gets to the other side. Eventually it does come to a stop because gravity is decelerating it now, but then it swings it back until it goes the other way and ends up right where it started. And as I'm sure you can imagine, this motion can go on back and forth indefinitely. So even though I didn't say it explicitly, what we really just saw is that this oscillation happens because the acceleration of our system depends on where it is. If our system is on the right side of the equilibrium position, the force of gravity will always accelerate it to the left, regardless of how it's moving at any given moment. And if the pendulum is to the left of the equilibrium position, then the force of gravity will always accelerate it to the right, regardless of how it's moving. And those dynamics are precisely what make the pendulum oscillate in the first place. Let's talk about a couple other examples that behave really similarly to the pendulum. For example, this doorstop on the bottom right has an equilibrium position when it's perfectly perpendicular to a wall, but if you were to flick it up so that the doorstop is in this position, there would be some sort of restorative force that pushes it back towards the center. Of course, as you might have experienced, oftentimes the door hinge shoots past the center, at which point the force connecting the doorstop to the wall immediately changes direction and begins to pull the doorstop back towards the center again. And those oscillations can also repeat indefinitely, and in fact it would repeat indefinitely if there were no friction involved in the real world. Friction is actually the only thing that makes the doorstop ever stop going back and forth. Now, the doorstop isn't the simplest system to analyze, because as you and I both know by now, it's easier to analyze a single particle than a solid object, but we can still get a pretty good picture of what's going on if we replace this system with the one at the top, where we keep the spring, but place all of the mass at a single point at the bottom. So the mass would be down here, and the spring would have negligible mass. In this case, what happens if you displace the mass from equilibrium, say you pull down on it here, you're actually stretching the spring, and the spring begins to exert its own restoring force that pushes the mass back to equilibrium. And as has been the story of these oscillations, the ball will shoot past the equilibrium because there's no friction or any other force to stop it there, and then by the time it gets to the other side, the spring is compressed, and the spring starts to exert a force on the mass downward that once again restores it back to this equilibrium position, except it overshoots, and so on and so forth. So I want to draw your attention to the two things that all of these oscillating systems have in common. The first is that all of these systems have some sort of restoring force. And a restoring force is simply a force that pushes to the right, which we'll call F greater than 0, when our system's position, which we'll call x, even though it doesn't have to be the x direction, is less than or to the left of its equilibrium position. And vice versa. The force pushes to the left when our position is to the right of the equilibrium position. So in other words, regardless of where our system is, this force that's being exerted on it is always pulling it back toward this point of equilibrium. And of course, at equilibrium, by definition, there's no force, and our object doesn't accelerate at all. Now, the physical source of this restoring force can obviously vary, right? In the case of the pendulum, it's gravity that acts to restore the pendulum back to its vertical position. Or in the case of our spring, it's all of the tension in the spring which provides the force to push or pull it back to equilibrium. But regardless of what the force is, it changes direction based on where our system is relative to that equilibrium point. The second thing that all of these oscillating systems have in common, which is really equivalent to this idea of a restoring force, is a potential minimum. Or in other words, a minimum in the potential energy of the system at the equilibrium point. If you've seen our episode on energy conservation, then you'll know that basically by definition, whenever a force is associated with a potential energy, it always pushes towards lower potential energy. So one way to capture this idea of a restoring force is to realize that if you look at your potential energy, which I'll call V, as a function of position, which I'll call x, then if we have a potential minimum at the equilibrium point, so here maybe instead of calling it x equals 0, I'll call it x equilibrium, then on both sides of that equilibrium point, we can realize that the potential energy has to be higher. Because if the potential energy is higher to the right of x equilibrium and to the left of that equilibrium position, then regardless of where our system is, the force will always push it toward lower potential energy. In other words, towards x equilibrium, which is exactly the behavior we saw from our restoring force. And you can see this description in terms of the energy of a system in action in all three of these oscillating systems. In the case of the pendulum, the gravitational potential energy is minimum when the pendulum is vertical and the mass is at its lowest position. But whenever it's raised, regardless of which direction it goes, the potential energy increases, just like in our picture. Similarly, for the doorstop and the spring, whichever direction it's pushed or pulled in, you increase the potential energy that's stored in the tension of that spring. And the restoring force will always push to reduce that potential energy by getting you back to the equilibrium position. So let's take these ideas and put some real numbers to them. The graph of potential energy we drew looked something like this. But the truth is, we don't know what the actual equation of potential energy looks like. It could be a parabola that goes up in both directions, but alternatively, it could be something completely different. You could probably come up with a system that has a potential energy curve that goes like some sort of cosine of x. In fact, there are infinitely many things that this potential could really be doing on the grand scheme of things and still look the same when you zoom into this equilibrium position. But as it turns out, that's not necessarily a bad thing. Because if we know that the oscillations around the equilibrium point are small, meaning we know that x goes back and forth, say, between this position and this position, and the difference between the potential over here, whether it goes up sharply or comes back down, becomes irrelevant, then we actually don't care what the potential looks like on the grand scheme of things, right? If our oscillations are small enough, all we care about is what it looks like next to that equilibrium point. And mathematically, through a process known as Taylor expansion, it turns out that, barring some specific exceptions, the vast majority of potentials that look like this near the equilibrium point can accurately be modeled as parabolas, meaning v of x is some number, I'll leave that blank there, times x squared. And in some cases, it's possible that the potential is exactly quadratic, but the point is that even if the potential isn't exactly quadratic, like if it's a cosine, as we said before, this equation will still hold approximately true for small x. In other words, small deviations from the equilibrium position. Now, when I first heard this claim, I was like, even if that's true, how small is small, right? It seems like such an arbitrary and vague word to use. How close do you have to be to equilibrium for this to be a good approximation? And that was quite an unsettling thought. But the truth is the answer is quite simple. This potential, if it's not exactly quadratic to start out with, will never be exactly quadratic in this approximation. But the smaller you make x, the smaller your oscillations are around the equilibrium point, the better of an approximation it'll be. So what we mean by small here is actually entirely up to the physicist, entirely up to how much precision the physicist wants in this sort of analysis. So with that subtlety out of the way, let's get back to thinking about this coefficient in front of the x squared term. Normally, I would just give it some variable name, like c to stand for a constant in front of the quadratic term. But for this analysis, I'm actually going to do something a little bit different. I'm going to give it the form of 1/2 m, the mass of our system, times some constant omega squared. Omega is a Greek letter that is just an arbitrary constant, just like c would have been otherwise. But calling this constant 1/2 m omega squared, as complicated as it might seem now, instead of just omega or just c or something like that, will actually make the math that we're about to do a little bit simpler, so just bear with me for now. Now, just to get all the subtleties out of the way, there are two more things we need to think about before we move on to analyzing these systems. The first is that x measures deviation from the equilibrium position, as I've drawn it here. So if you want x to be a physical parameter that measures the true position of your system, then what you should really be writing is 1/2 m omega squared times the difference between x and the equilibrium position squared. But obviously this is a much more cumbersome and inconvenient form of the potential energy to work with, so in most cases you should really try to set the position of that equilibrium point to x equals 0. That way you don't have to worry about this term, and you can simply work with the simpler form of the potential that we've written up here. Finally, as you might remember from our episode on conservation of energy, this potential energy is only defined up to a constant, meaning we can tack on a term that looks like plus V0 plus some number, and that wouldn't change the physics of the system at all. What V0 represents here is the potential energy at the equilibrium position, at x equals 0. And again, the most convenient thing to do is to simply define your potential energy to be 0 at that equilibrium position, so that once again, this term can be ignored, and you're left with this simple parabolic equation. So let's cut to the chase. What does this potential actually tell us? Well, most importantly, it tells us precisely what the restoring force is equal to on our system. Remember that the force as a function of position is equal to the derivative of the potential energy with respect to x, with an added minus sign. I always forget that minus sign, and it's always a bad thing. Don't forget that minus sign. Anyway, if we include that minus sign, what we realize when we take this derivative is that the force is equal to minus m omega squared x. And of course, since we're treating the system in one dimension, this force is in the x direction, so we can just change x to x vector to reflect the direction of that force. What you see is the same property that we talked about earlier about restoring forces, namely that if x is a positive vector, if x is to the right of the equilibrium position, the force will be negative. It'll push it to the left. And if x is to the left, meaning x is negative, then the force itself will be positive, pushing it to the right. And in particular, what we've learned when we're dealing with a potential that has a minimum like this is that the force doesn't just change direction depending on where our system is relative to the equilibrium point, but it also gets stronger the farther away from equilibrium we are. This general relationship that the force is proportional to minus x is known as Hooke's law. And any system that obeys Hooke's law, which effectively refers to any system whose potential energy is approximately quadratic, any system that obeys Hooke's law is said to be in simple harmonic motion, right? So simple harmonic motion, or SHM, is a specific kind of oscillation where the force doesn't just change direction depending on whether you're to the left or right of equilibrium, but it's related to the system's position in this particular way. Namely, it has a linear relationship. So we've set up the physics to describe a very general system here, but obviously we can't get an exact trajectory for any specific system until we know what the constant omega squared actually is. Right? Without that information, we don't know how strong our forces are, even if we do know that they're going to be proportional to x. So how do we find this constant of proportionality for specific systems? Well, let's look at one at a time. Let's start with the pendulum, and let's think about the forces that are acting on it in the x direction, namely the horizontal direction here. We know that gravity pulls down with a strength mg, and we know that we can further separate this force into two components, one that goes along the direction of the string, and one that goes perpendicular that direction, which sum to give us the net force mg downwards. If we know the angle over here that the pendulum makes with the vertical, then we know that the components of this force are mg cosine theta, pointing along the string, and mg sine theta, pointing perpendicular to the string. And in addition to that, we know that whatever force is going along the string, this mg cosine theta, has to be cancelled out by the tension force going up the string. So this has to be also mg cosine theta, because the mass can never accelerate in the direction of the string. Otherwise, the string's length wouldn't be fixed and our whole problem is broken. So the only force we need to worry about in this case is the mg sine theta component acting perpendicular to the string. So how much of that component actually pushes in the x direction? Well, if we draw out this diagram and break it into components along the x direction and along the y direction, then this net force has to be mg sine theta. This angle here is going to be theta, and you can double check that geometrically. And so the component of the force acting to the left, or restoring it to equilibrium along the x-axis, is going to be mg sine theta times cosine theta. Now remember, our goal is to extract this coefficient over here. We need to figure out what m omega squared is, and the way we're trying to do that is to write the force as some number times the position x. So let's see if we can rewrite all of these sine thetas and cosine thetas in terms of x. If we know the length of the pendulum, the length of this string right here, then we automatically have the relationship that the x-coordinate of our system, of our pendulum, is L sine theta. That just comes out of the geometry. And so that means the force in the x direction, which we previously found to be mg sine theta cosine theta, can be rewritten as mg. Now we replace sine theta with x over L, and then we keep the cosine theta. So this is close. We now have something proportional to x, but it's not just a constant proportional to x, because cosine theta is subject to change as well. Fortunately, if theta is a small number, meaning if our oscillations are sufficiently close to the equilibrium position, as we were talking about before, cosine theta is actually going to be roughly 1. So we can approximate this force as mg over L times x. That's it. Now, obviously, this is just the magnitude of the force. We know from the picture that it's going to be acting to the left. So if we wanted to write this as a vector, fx vector would be pointing in minus the x direction. And then by comparing it with our equation from Hooke's law, we can tell that if we have m omega squared be mg over L, then our force is exactly in the form that we wanted it to have. In other words, we found what omega squared is. We found that omega squared is g over L. Now, I did this by looking at the force and trying to fit this form, that force is proportional to x, but you could have gotten the same answer by looking at the potential energy of this pendulum and making it fit the form of v of x equals 1/2 m omega squared x squared. You would have gotten the same exact answer for what omega squared has to be. So now let's think about another example system, this mass on a spring. In practice, springs are complicated, and we don't analyze every single little force that exists between the spring and whatever mass we're looking at. Instead, it's an empirical fact for most springs that the force is indeed proportional to minus x, and that proportionality constant is called the spring constant, k, and k just measures how stiff the spring is. So if k is very large, you get a large force, a large restoring force, just by compressing or stretching it a little bit, so the spring is very stiff. If k is a very small number, then you can compress it a lot or stretch it a lot without experiencing a super strong force. But regardless, k is going to be a positive number, and you'll always have a restoring force that pushes this system back to equilibrium. You can tell by comparing it to the form we wrote down before that this coefficient k, the spring constant, is going to equal m omega squared. And so for this mass on a spring system, omega squared will be k over m. Now you might ask, if this mass on a spring is hanging vertically, as I've drawn it here, why don't we consider gravity as a force acting on the system? Why do we only consider the force of the spring on the mass? And the answer is that gravity doesn't actually change the dynamics of the system. The presence of gravity only changes the equilibrium position. And you can see that quantitatively. If you write down F equals minus kx minus mg, then you can reformulate this as minus k times, in parentheses, x plus mg over k, which is exactly the form of a restoring force. It's minus k times some position, except this position isn't just the variable x you started out with, it's actually the distance from the position minus mg over k. So this is simply x minus a new equilibrium position, where the new equilibrium position is minus mg over k. Which makes sense. Gravity pulls the system down, so its equilibrium position is at a lower x, right? In this case, we were defining x to be this direction, so lower x means closer to the ground. But apart from changing that equilibrium position, the presence of gravity didn't actually do anything to the forces acting on our system. Because once the spring has reached this new equilibrium position, the little bit of tension coming from the spring pulling the mass back up just cancels out the force of gravity pulling it down. And after that cancellation has happened, we can treat the system as a mass on a spring without even considering gravity at all. So what we've done here is lay the framework for figuring out what the force is for various systems that are going to oscillate. So now what we have to do is take that force and actually do kinematics, right? The force gives us an acceleration, and kinematics takes that acceleration to our system's trajectory over time. So let's write this out. We have that force is equal to, and I'll write this in vector form, minus m omega squared x. And as we just talked about, omega squared is a constant that you can find for whatever specific system you're dealing with. But this is a very general analysis that covers many different systems, so we're leaving it as a variable. This tells us that the acceleration of our system is going to be minus omega squared x. So already you can see why it becomes convenient that we defined our constant as m omega squared and not just omega squared, because now our equation for the acceleration is just a little bit simpler. Now, normally to turn this into a trajectory, we would first want to find the velocity of our system, which is the initial velocity, v0, plus the integral from 0 to t of the acceleration, which is minus omega squared x of t, right? Because x is a function of time, because our system is moving, dt. Obviously, we run into a problem here, because we don't know x of t yet. That's what we were trying to find to begin with. So the straightforward kinematic approach of just integrating acceleration to find the trajectory won't work anymore, and instead, we'll need to use some more clever methods. The trick here is to realize that acceleration is just the second derivative of position with respect to time, d squared x dt squared. And we're setting that equal to minus omega squared x. And if you're clever and you stare at this for a while, you can think about different functions, x of t, that when you take two derivatives, give you something that's proportional to the function you started out with, but now with a minus sign and maybe some coefficient out front. And what you'll realize is there are actually two such functions that are independent of each other. The first is x of t, call it x1 of t, is the sine of omega t. So if you take one derivative, you get omega cosine omega t, and if you take a second derivative, you get minus omega squared sine omega t, which is minus omega squared x, exactly as we wanted. The second solution is, unsurprisingly, x2 of t is just cosine of omega t. So you can check for yourself that if you take two derivatives, you'll get cosine of omega t back, but now multiplied by minus omega squared. And what also turns out to be true is that if you add these solutions together any number of times, so you have any number of sine omega t's plus any other number of cosine omega t's, and you set that equal to your x of t, that will also be a solution to the equation we had before, that if you take two time derivatives, you'll get minus omega squared times x. Now you might wonder, are there more solutions? Sure, we've guessed two of them, but what if there's a third that we haven't come up with? And luckily, there's a mathematical theorem that says if our equation of motion only involves two derivatives of x, then there are only two independent solutions to that equation. So once we found the sine and the cosine, we can consider ourselves done. At this point, you can also see why we chose our constant at the very beginning to have an omega squared in it instead of just an omega, because we ended up having to take the square root of that constant when we put it into our sine and cosine functions. So if we chose our constant to be omega instead of omega squared, then all of these sines and cosines would have a square root of omega times t in it. And having a square root in your trig functions is just bad form, let's be real here. So ultimately, this is what we've accomplished. We have found the most general possible solution for the position of our system as a function of time, assuming it has an approximately quadratic potential energy. Of course, even though we know how to find omega, we just talked about that on the last slide, we still don't know what A and B necessarily are, so we still don't have a complete trajectory for our system. But in fact, A and B are just a couple of physical parameters that control the properties of our oscillations. For example, if A and B are bigger, then obviously the oscillations have more amplitude. That is, the pendulum swings wider from side to side, or the mass on a spring is compressed and stretched a larger distance with every oscillation. At the same time, if A is much bigger than B, then we know that our oscillations basically look like a sine curve, meaning that we start out at x equals 0 with some initial speed that takes us away from equilibrium, whereas if B was greater than A, then our position would be a cosine curve, which means we start out far from equilibrium, but with no slope, with no speed. So in that sense, A and B control not just the amplitude of oscillations, but also the phase of the oscillation, which just means where do you start out? Do you start out moving, or do you start out far away from equilibrium? There's another way of writing this equation, which captures these two parameters more explicitly. And that's, we can say x of t is equal to some other constant, c, times the cosine, or the sine, but usually you choose cosine, of omega times not t, but t minus t0. And replacing t with t minus t0, where t0 is a constant that we're still free to choose, lets us shift the curve left and right depending on how we actually start out. And c now is just one number that controls our amplitude. And if you remember some of your trig identities, then you can, with some work, figure out that these two equations are related to each other by c squared equals a squared plus b squared. And this number omega t0 is the arctangent of the ratio b over a. So those two properties are generally not something that you have to memorize, but it's helpful to see how the second form of our position function over time is related to the first form. Now, regardless of which form of the trajectory we want to use, whether it's this form over here in terms of sines and cosines, or this form over here in terms of an amplitude and a phase shift, we're still left with two variables, either a and b or c and t0, that we have to find values for before we completely know what our system is doing and how it's moving over time. Right? All we've done so far is to realize that any solution to the equation a equals minus omega squared x has to have this form, but we haven't pinned down which of these solutions our system is actually going to take on. So to figure out what these constants actually are, we have to know something about our system to begin with. And that's not entirely surprising. Even when we did constant acceleration kinematics, we couldn't find our trajectory without knowing the initial position and the initial velocity of our system. And in fact, if we know those two things, if we know x of 0 and we know v of 0, then we can immediately figure out a and b. And that's just because if we plug in t equals 0 into this equation, we get x of 0 equals a times sine of 0, which goes away because sine of 0 is 0, plus b times cosine of 0, and cosine of 0 is 1. So x of 0 is just going to be equal to b in this case. And v of 0, well, to find the velocity as a function of time, all we need to do is take a derivative. So the first term will give us a omega cosine omega t, which turns out to be a omega times 1 when t equals 0. And the second term will give us something proportional to sine omega t, which goes away when t equals 0. So just by knowing x of 0 and v of 0 are initial conditions, we can figure out that b is equal to that initial position, and a is equal to the initial velocity divided by omega. Now, the second form of our trajectory, c cosine omega t minus t0, that's useful if what we know beforehand is the amplitude, x maximum, the maximum distance or the maximum deviation from equilibrium that our system will ever take on, and we know the time at which that maximum occurs, or any one of the times at which that maximum occurs, since it's oscillatory motion. And in fact, if we know those two things, then these constants are just c equals x max, and t0 is that time at which the system is at its maximum position. So depending on which kinds of initial conditions you know, one of these forms or the other might be more convenient to express your trajectory. And once we know the position as a function of time, we can find the velocity and acceleration as a function of time too, just by taking derivatives. If we work with the second form, then the velocity as a function of time will be minus c omega times the sine of omega t minus t0, just from taking one derivative. And the acceleration as a function of time will be minus c omega squared cosine of omega t minus t0. And what you'll notice from these equations is that the acceleration and the position both trace out cosine curves over time, meaning when position is 0, acceleration will be 0. That's at the equilibrium point where there is no restoring force. And when position is maximum at the amplitude, acceleration is also maximum. That's when the restoring force is strongest. On the other hand, velocity traces out a sine curve, which is maximum when x is minimum, and minimum when x is maximum. This also makes sense, because at equilibrium, when x is 0, velocity is supposed to be high, and at the endpoints, when x is maximum, your system is supposed to stop moving temporarily as it turns around. So that's the big picture of what simple harmonic oscillation looks like. Let's talk about one last feature of simple harmonic motion, and that's where the energy in our system is over time. I've copied down here two equations that we just derived for the position over time and velocity over time of our system. This symbol over here, x with a dot on it, that's just a shorthand for writing dx dt. The dot stands for the time derivative, and that's a convention introduced by Isaac Newton himself. And the reason I'm using it here is so that we don't confuse v of t velocity for v of t potential energy. This way it's unambiguous. Anyway, with these two equations in mind, we can automatically write down both the potential energy and the kinetic energy of our system at any given time. From the position, we can find the potential energy because we know that the potential energy is 1/2 m omega squared x squared. That's what we stipulated at the start of this whole thing. So if we plug in x, what we end up with is 1/2 m omega squared c squared cosine squared of omega t minus t0. Similarly, the potential energy is 1/2 m times the velocity, or x dot squared. And if we plug in x dot, we get 1/2 m omega squared c squared times sine squared of omega t minus t0. So one thing you can automatically notice is that if you take the sum of kinetic plus potential energy, you're going to get a common factor of 1/2 m omega squared c squared, regardless of what any of the parameters are. And the rest of it, which is cosine squared of something plus sine squared of something, is just going to be 1 by the trigonometric identity, which means that, as we expected, the mechanical energy of the system, the sum of potential and kinetic energies, is going to be constant throughout all of time. But, as we've already seen, that doesn't mean that the kinetic energy and potential energy can't individually change over time. So let's make a plot of a specific example where we choose t0 to be 0 for simplicity, and then we plot the potential energy and the kinetic energy over time. So let's draw some energy axis over here, and let's draw the time axis over here. And I'm not going to worry about the amplitudes of these energies in this sketch. I just want to show you the general time dependence. We know that the potential energy, which I'll draw in a red color, basically looks like a cosine squared function. And a cosine squared function is always positive, and a cosine squared function starts at a maximum. It starts up here, and then oscillates back and forth, but always remains positive because it's a squared function. So it'll look something like this for t greater than 0, and we can also extrapolate for t less than 0. It'll look something like that. Now, I may not have drawn it too well here, but all of these peaks and troughs are supposed to be spaced equally far apart, just like any cosine function would, but here we're just squaring it. Similarly, the sine squared function starts at 0, but also always remains positive. So the oscillations of the kinetic energy will look like this. And again, for t less than 0, they'll do something very similar. And of course, what you'll notice is that if you add the kinetic and potential energies, so maybe I'll label these V and T, when you add them together, you actually get a constant mechanical energy that bounds them from the top over here. So this is T plus V. So this is a more visual form of understanding how energy is conserved but changes form as the oscillation takes place between potential energy at the far amplitudes and kinetic energy when the system is near the equilibrium position but moving quickly. In fact, we can label some of these points. So over here, at this position, this is where the system is at the right amplitude. Then at this time, the position is going to be at equilibrium, right? And we know that because the kinetic energy is maximized there. At the next point, all the way over here, we're going to have our left amplitude. And then we're going to go back to equilibrium, and so on and so forth. So with all that said, let's look back and summarize all of the important things we talked about in this episode. We started out by claiming that anything that's going to undergo simple harmonic motion, by definition, has to have a potential that's quadratic. And the coefficient that we chose to put in front of that potential is 1/2 m omega squared. Any system that has a quadratic potential can equivalently be said to have a linear force relation, which we called Hooke's law, and the coefficient of proportionality between the force and position was minus m omega squared. Now, this quantity omega squared is just a constant that can be different for different systems, and in this episode we found that omega squared was equal to g over L for pendulums, and was equal to k over m for a mass on a spring, where k is just the spring constant that measures how stiff the spring is. Now, this quantity omega characterizes how quickly our system oscillates over time. If we look at any of these equations that we derived for position, velocity, or acceleration over time, we see that the larger omega is, the less time it will take for a full cycle to be completed, for whichever one of these variables we're talking about. That means that omega measures the angular frequency of our system, or in other words, how many radians per second our system is covering as it oscillates. Another common measure for how quickly a system is oscillating isn't how many radians per second it covers, but how many cycles per second it covers. That's called the cyclic frequency, and it's measured in hertz and denoted by the letter F. And the relationship between how many cycles you cover and how many radians you cover is just a factor of 2 pi. So if you know how many radians you cover, which is omega every second, and you divide that by 2 pi, you get the number of cycles you cover every second. There's another quantity called the period, t, and instead of telling you how many cycles per second you cover, like the frequency does, t is a measure of how many seconds per cycle it takes, how many seconds it takes to cover each cycle. And to get that, you just take 1 over the cyclic frequency to get from cycles per second to seconds per cycle. Finally, the last thing we talked about was energy, and although you can always derive the kinetic and potential energies from their respective equations, one thing that might be important to know is that their sum is always going to be constant, because there's no dissipation of energy into heat or anything like that, and it will equal 1/2 m omega squared c squared, whatever our coefficient c is determined to be from initial conditions. So I hope you guys enjoyed this episode. I hope you guys learned something about oscillations. As always, if you have any questions, drop them in the comments down below, and I'll see you in the next one.